Now, we've already considered how we can analyse displacement graphs to look at the velocity and the acceleration graphs that would go with them. And we know that each time we go from a displacement to velocity to acceleration, we need to differentiate once each time. But it can be a lot trickier when you're given a velocity graph and you have to understand what it means. Now, going from velocity to acceleration, we differentiate, and that's a little bit more straightforward. Of course, if we've got the equations for any of these, we can use our calculus to get the equations for the others, as long as we've got a few clues. And then we can graph those just using our graphing skills. But here, we don't have an equation for this, we just have to consider some things we know about gradient to try and graph the other two. And this is a really tricky type of a problem. Now, when you did your flight path assignments in year 11, you made a flight path and then you differentiated it twice just by looking at the gradient. So let's do that to get from velocity down to acceleration. Now, I've put some key points of interest here. We've got the two flat spots or stationary points where the gradient is 0. So if the acceleration is just the gradient of the velocity, in other words, the first derivative of the velocity, then here and here, I'm going to have values of 0. So that's two spots on my graph. Now I just need to consider the gradient of this curve at all points and roughly graph something that matches up. So I've got a positive gradient all the way along here. Here is a point of inflection I've put on my graph because it's showing the steepest part of my curve. So this is where the gradient is the most positive, and then it's 0 again. So here, lining up with this point is where it's most positive. This should be a high point on my curve, or a stationary point, and I'm going to be going along like this. Nothing especially is happening at the intercepts here on this graph, because going from this one to this one, all I'm really doing is looking at the gradient. The gradient is 0, then it's positive, and then it's really positive, as big as it's going to get, and then it goes negative again. Sorry, it's still positive, but it's going down until now it's 0. And that's the same thing that's happening here. Now from there on, the gradient is negative and keeps on going down until it gets quite steep. So at this point, this gradient curve is just going to keep on heading downwards. Now going the other way around, I need to sort of work backwards and think, what sort of curve would I be able to analyse the gradient of and get this? Well, the gradient of my original curve must have been negative between this x value and this x value. Usually this sort of question you'll be given some initial condition like when x equals 0, t equals 0. So we're going to start there. We've been given that as a starting point. And we need to have a negative gradient on this curve for the first bit. Now the fact that we've got intercepts here and here, this means that the gradient of this curve was 0. So it must be a flat spot. So if it was going down to start with, because we had a negative gradient, then we must be at a flat spot by the time we are in line with that. So I'm going to make that a minimum turning point. I'm going to be back to having a gradient of 0 by the time I'm here. But where will it be in space? Well, it seems like between here and all the way over to here, I've got a positive velocity. Now that means that I must have had a positive change in my displacement. So when I'm graphing the displacement, it must be going up and up, right? Now, the other key point here is that this is when my velocity is the highest. And that means that we must have the greatest change in our displacement at that point. So if we're going to, from here, go all the way up, it's going to look something like this, I think. Now, just checking if this makes sense. The gradient is 0 here and here, yes, and yes. The gradient is negative only between here and here, yep, negative, there and there. From here on, it's positive, yep. And it's the steepest it's going to get here at a point of inflection. So that's the highest value of the gradient of the displacement, which is the velocity, and that equates to this. So in other words, a point of inflection on one curve will be a stationary point on the next. And a stationary point on this one will equate to an intercept on the horizontal axis on the next one. And that's one way that you can work from one graph backwards or forwards to find something suitable for the others. Now, because with these graphs we were just sort of guessing using shapes, we didn't actually have any equations to work with, it's impossible to know what the highest power of t might have been, because of course x and v and a are all equations that have t in them. So whether it's t to the power of 5 being the highest power, and then you get t to the power of 4, t to the power of 3, or whether you have a cubic curve that becomes a parabola that becomes a diagonal line, or a parabola that becomes a diagonal line that becomes a horizontal line, we've seen that every time we differentiate something, we get a power of t that's one smaller each time. Now here, it's impossible to know what those powers might have been. And in fact, this could just be one small section of a very long and complicated formula. It could be to the power of 7, 6, and 5 for all I know. So that's why it's hard to get the shapes exactly right, and there's a certain amount of guesswork. But what we find out does give us valuable information, and it reinforces some things that we've already learned. For example, we've said that acceleration is the second derivative of displacement. So we know that velocity is just looking at what the gradient is on this graph. But acceleration is looking at what the concavity is on this graph. And we can see quite clearly here that if this is a point of inflection, this graph is concave up from this point to this point and concave down from there on. That would tell us that acceleration is positive in this section and negative here. Well, sure enough, we have a positive acceleration right up to that point, and from there it's negative. So they agree with each other to some extent. Now, other things that we can take out of looking at a velocity graph. Remember that when v equals 0, our particle or whatever it is that is moving is not going anywhere. For a moment, it's stationary. If velocity is positive, then it's moving up if it's in the case of things moving up or down, or it's going to the right if we're on a number line and something's moving left and right. And if velocity is negative, then it means that we're moving down or perhaps left, depending on the context. So if we looked at these graphs again and then thought about what story it tells, if we imagined that this is actually a particle moving along a number line, let's look at what's actually happening. Well, this tells us where it is at any one point. It's the displacement. So it starts at 0. We can imagine a number line here. Let's draw it out. And then if we had some values in here, obviously we could make up a bit of a better story. So we can put some in just to sort of see what's happening. Perhaps it's going down to -2 here, and up here it's 1, 2, 3, moving up again. So it takes a couple of seconds perhaps before it's moved down to -2. So it begins by going this way. And then when it gets to -2, it turns around and goes back up to 0, and this time keeps on going through the origin and onwards to higher numbers. So this is a particle that's going backwards and then forwards. Now, does this agree with other things that we've seen? Well, as it goes backwards, it's going to turn around at -2. At its turnaround point, it will be stopped for a moment, won't it? So that makes sense here that the velocity was 0 at that turnaround point. We've also seen that as it gets up to, let's call this 3 on the number line, it's going to potentially be stopped again because look, the velocity there is 0. So it hasn't yet turned around on our graph, but perhaps it's about to turn around when it gets to 3 and go back the other way. And our acceleration is positive, and then it is negative. Our velocity starts off being negative. Well, that makes sense because we're going backwards. But once we make our turnaround point, then the velocity is positive. And in fact, it reaches its most positive. In fact, we're going the fastest here, where we're somewhere in between -2 and our next turnaround point. That makes sense. If something's just turned around to stop to turn around, and then it gets going again, it makes sense it's going to be going quite fast in the middle of that section before it slows down again to stop and then go back the other way. So some simple skills there to try and tell a story and make sense of what your graphs mean and what your equations mean.